Hello and welcome to Toddcast number 58. We're zipping through the carbonyl and alcohol introduction. So just to date, we've gone over oxidation reduction. We've looked at oxidizing agents like CrO3, KMnO4. We've looked at reducing agents like sodium borohydride, lithium aluminum hydride. And then probably most importantly of all, we looked at the Grignard reaction, which is a reductive reaction where carbonyl is converted to an alcohol through the addition of an alkyl group of some sort. And so I want to just sort of summarize this all into one grouping because as you start to do more and more reactions, it can get really, really overwhelming. So organizing them. So for alkenes, we did spider charts, put some reactant in the middle and spiraled or had offshoots on all of it in different directions of different reactions it could undergo. And then keywords to help to remember certain mnemonics, know what reagents do what. For this is probably a linear rather than a spider chart to consider. And so on the left-hand side, I'm going to have my alcohols. On the right-hand side, I'm going to have the oxidized carbonyl product. And we're going to hopefully summarize exactly what can happen with all these and just have, at least have an idea of what reagents we would use. So I'm going to have alcohols that are primary, secondary, and tertiary. And the cool little shortcut you can tell is oxidation, as mentioned, the gain of bonds to O, but it's also the loss of bonds to H. So if you look at the alcohol and see how many H's are on the carbon, you can quickly assess how much it can be oxidized. There are two bonds to H, so there are two H's that can be lost, so there's two oxidations. The first one to an aldehyde, second one to a carboxylic acid. For secondary alcohol, there is only one H on the carbon, oxyphilic carbon, so it can only be oxidized once. Tertiary alcohol, there are no H's, it cannot be oxidized. So you oxidize in this direction, reduce in this other direction. Grignard is a special case of where I add an extra R group. So aldehyde has one R, the alcohol it forms is secondary has two. Ketone has two, the Grignard product has three. So I want to look at that H again. So primary alcohols have two H's to lose, so they can be oxidized twice. First to the aldehyde, from 2 to 1, so it lost one of those H's, and then on to the carboxylic acid. Note that I can oxidize it here by using what's known as PCC, oxidizing agent, and then this other one I can use CrO3 in acid, or I can use KMnO4 in base. Okay, so you perhaps have those memorized. Reduction, sodium borohydride, if it's the aldehyde, NaBH4 and whatever else follows with it. But in order to go all the way across, I need lithium aluminum hydride. So lithium hydride is the more reactive species, so the one that reacts with the less reactive carbonyl. Okay, Grignard, MgBr added to whatever R group you want to add on in an aprotic, aka ether solvent. Okay, secondary, only one H lose, so only one oxidation step. And again, we can use CrO3 and acid. We can use KMnO4 and base. And as we go, we'll keep on adding other reactions. So for specialized conditions, acid and base are specialized. But for other specialized conditions, we'll develop specialized reagents as needed. But it has one H lose, so you get a ketone to go back the other way. I'm going to put sodium borohydride because, again, my goal, use the least reactive reagent I can. No H's to lose. Tertiary alcohols do not oxidize. At least not by traditional methods. You can insert O's into bonds by extreme reactions, but for what we're dealing in this class, pretty much that's it. Oxidizing agents, rich in O, poor in H, hence CrO3 and acid. KMnO4 in base. Reducing agents, lithium hydride, highly reactive, sodium borohydride, not as reactive. You need to memorize those. There might be a few other ones that pop up, but you need to know that. In the Grignard, RMGBr or RMGCl in an ether. Has to be done in an ether. Again, cannot have any protic hydrogens, any even weakly acidic protons will destroy your Grignard reagent. Okay, so pretty good summary. So let's see how we do. Oxidation of primary alcohol into an aldehyde involves all of the following. So first off, primary alcohol, OH on the first carbon, so two H's, an OH, and an R. You are losing one of the H's. So I'm going to lose this H, let's say, and this O. H is just going to become an O in the end. So H, actually, let me make that a little prettier. So when I use pyridine, it stops it, it poisons it. So pyridine acts as a poison to stop it from going to the carboxylic acid, stops at the aldehyde. So we definitely need to use pyridine. That's a true statement. Okay. We gain a bond to O with the oxyphilic carbon. Oxyphilic meaning the one that's loving of oxygen. So if it has one bond to O, it must be the one that loves oxygen. Now it goes up to two. That's a true statement. You can flat out just see it in the picture. One bond to O, two bonds to O. An increase in the oxidation state. Absolutely. So let me just double check. 0 and 0, plus minus, minus plus, minus plus, minus 1 to start. 0, 0, plus minus, minus, minus plus, plus 1 to start. Minus 1 and plus 1 differ by 2 electrons. Absolutely, positively true. So it should have made sense that I lost a bond to O and gained a bond to H. That's a 2 electron transfer change, so minus 1 to plus 1. And then finally, loss of a chiral center. Nope, 2 identical H's. So it didn't work out that way. So you can learn an awful lot from wrong answers or right answers, both, on multiple choice questions. And this is that weird case where 3 things are true, 1 is false. But still, going through each one makes you review. So actually a pretty powerful tool for reviewing. Best answer, the false choice, is D. So time to figure out, how do I make ketones less reactive? So it's the pi bond that's doing the reacting. So if you can somehow get rid of a pi bond, you're set. So little things going to consider. If I want to oxidize this, this is already reacted. This one has not. So I need to choose conditions to react here and not here. But if I want to react with this and I don't want this to attack, then I have to turn this into something else. So we do specific reactions that only react with the one single functional group we want to save. So by putting something protective on here, so you've done this in life all the time. You put on a glove to work in labs so you don't get chemicals on your hands. They are protective equipment. So protecting, I put something on the OH to cover it up. It ends up that if I were to do this Grignard reaction as such, it would actually deprotonate that O and I'd get absolutely nothing. So I would not get this reaction that I want to get. This would, I mean, this, I wouldn't get the reaction I want. I wouldn't add this to the ester like I'd hoped. I would deprotonate that O. To avoid the deprotonation of the O, we have to go a different route. So if we protect this OH and it ends up, oxygen loves silicon, likes to make sand. So I'm going to put this compound, the O is going to attack the silicon, kick out the chlorine. And when I do, I get trimethylsilane on an O. So O trimethylsilane. So now this is protected because it's no longer an OH. So OH reactions aren't going to happen. So now if I add a Grignard to this, I'm going to add 2 equivalents. I'm going to emphasize that, 2 equivalents, because it's an ester and esters add twice. So it's going to add 2 equivalents, CH2, CH3. It's going to go on twice. One's there, one's there. With my OH, then I got to take it off. Random fun fact, you etch glass using hydrofluoric acid, HF. So it isn't the H that actually is reactive, it's the fluorine. Fluorine has an even higher affinity for silicon than oxygen. So just like oxygen went on to silicon and kicked out chlorine, fluorine will go on and kick out oxygen. So there are a couple different versions of it. What you add, I'm going to put HF, where you get rid of it. HF is kind of nasty, dangerous stuff. So it usually is for the sake of putting it into the solution. not have it too corrosive or highly reactive. A lot of times we may end up doing something like this. Plus charge there, F minus there. So this can also, alkyl group can help pull it in the solution. So as long as I see the F, so anything ending in F short of profanity is acceptable. Okay, so didn't mean to erase that. So protecting groups for carbonyls. The pi bond is the reactive one. So if I want to only react with the alcohol and not react with the carbonyl, then I need to add a protecting group. Okay, this is going to get a little potentially tricky because an alcohol, we're going to learn, can attack a carbonyl. But if it did, it would form a 1, 2, 3, 4-member ring, which is unstable. So it would prefer to form something a little bit bigger. So we'll see how this works out. Hopefully this is all going to work out for me. So I mentioned real briefly that Bart-Simpson protects our carbonyls, protects our ketones. So somehow, some way, I need to see if I recognize that functional group anywhere. And lo and behold, there it is. So I got to get that compound on there. So let's see how we put Bart on here. I'm going to also try to bias it a little bit by coloring it in blue. These are the atoms we do not need on there. So a lot of times, from this point on, you're going to start noticing common side products that we throw away will be H, H, and O, or water. So if we're going to find the missing water, and so I'm going to cheat and do this at first. By no means have anything to do with the actual mechanism. So if I can get rid of the O I used to have, and the H's I used to have up here, so those were the ones that fit in here. And I just play connect the bonds. Ta-da. It's an uglier version of Bart-Simpson, but it's going to go on. So that part of the ring system connected to that carbon, it's still 2 bonds to O like it had. Each of these still have 1 bond to O. So it's working out. And the side product is water. Okay, so let's look at it mechanistically. I looked at it pictorially. I looked at it kind of demonically, if you will. So now to consider what's actually happening. So Bart-Simpson has jumped on to protect us. Check. Water is formed. That's our side product. Check. So now to figure out how this mechanism works. So first and foremost, when you use an acidic system, it's going to protonate the most basic site. Ends up that's this O. And when it does, it now makes this carbonyl more susceptible. And if you do this twice, protonates it once to make OH, another time make water, that's what comes off. This other one is going to. So let me draw a second step. This is, again, something that we'll go into in more detail soon. I just want to emphasize that I'm getting 2 new bonds. So that's one of the bonds I'm getting. And that's the other bond I'm getting. So it goes on one at a time. One OH goes on, protonate goes in, second one protonate, water leaves, and this goes on. Okay, so if I can protect it, I can keep it from reacting. Okay, so let's say I have this compound. I have a ester and a ketone. If I want this to react, it actually is going to preferentially react with the ketone, but there is an outside chance that this can actually go in and substitute for this O, and you can end up getting some issues. So I have to be careful because in acidic conditions, esters are somewhat reactive. Esters react with acid water. So this is not a great reaction. It's hopefully I can work my way around it, but I still can protect it. So the probably better option, choose a reaction condition that you don't have to protect it. So this one, because of potential side reactions and issues, when I put it on, take it off, I have ketones going to react, but I also going to have the ester that can react. Instead, let's say I only want to reduce the ketone and not touch the ester, then I choose the least reactive reagent I can, barely get by, aim low. So if I use sodium borohydride, it only reacts with a ketone and does not react with the ester, so I can reduce it down. So note that it's this one plus the enantiomer. So sometimes no need to protect. So if I was protecting this to carry out this reaction, that was pointless. You only need to protect when you have a case of two competing sites. So if I were to do a Grignard or some sort of reaction at this alcohol, or I'm going to do some sort of reaction that potentially reacts with a ketone or aldehyde, I got to protect it. If I want to do a reaction on the ketone, I need to protect the ester. If I need to do a reaction on the ester, I need to protect the ketone. This is going to be a little bit trickier, but doable. Or if I need to do a reaction at one site and it just so happens it's the more reactive site than the other, then I luck out. Okay, so no protection needed because it only reacts at the one side I want. Um, so using it in a synthesis. So let's see the big picture. Let's try it all together. So let's say I want to go from this compound, this 1, 2, 3, 4, 5, 6 carbon. So it is, I guess we're going to call it a ketone, but it's going to be 1-hydroxy hexane 5-ol, or hexane 5-ol, excuse me. So have that. And I want to put on this thing. So let's see what I've done. I've added a carbon-carbon bond right here. So I know I have to have some sort of Grignard. So I'm going to make up a to-do list. The first thing I should recognize, you've added to carbon chain. Grignard is the only way we know how to do it as of today. I have also then, and pay attention, I had two H's here. Now I only have one. So I've lost an H. Losing an H means it's an oxidation. Losing only one H means I have to take it from the alcohol, primary alcohol, to an aldehyde. Otherwise, it would have gone to carboxylic acid, and the Grignard wouldn't have worked with it. Doesn't work with acidic compounds. Okay, but I have two functional groups, and if I want to do a Grignard here, I got to convert this into something reactive. Problem is, this is already reactive with the Grignard. So I have to protect this group first. So I have to protect it, and then I have to get the compound back to the way I want it, so I need to deprotect. So this was just years and years ago. There was, I mean, safety videos were just a thing that had to be watched in lab. This was long before the internet where you had to get to watch them at home. But one of the videos, the one on early on in every lab course, talked about personal protective equipment, just safety gear back then, goggles, gloves, lab coat. And they said, first thing you do when you go in, put on your safety gear. Last thing you do when you leave, take your safety gear off. So when you walk in the door, protect yourself. When you leave, deprotect yourself. The first step, always protect yourself. Always practice safe chemistry by putting your protective gear on first thing when you go in, do your chemistry, and then when you leave, you can take your protective gear off. But first step, so this is non-sequential, but I now know this has to be first, this has to be last. Okay, so to do sequential, protect first. So you protect it by having Bart Simpson protect your ketone. Second step, doesn't react with an alcohol, so we have to turn it into something reactive. So lose an H means we have to oxidize it, PCC. Third, now we're going to do the Grignard step, add it. Knew that had to be third because can't be fourth because that's deprotect. And then last step, deprotect. So perfect. So we took our observation of what we had to do. We had to oxidize, we had to add a Grignard, we had to protect and deprotect. We just put it randomly, and then we worried about the sequence. So protecting the ketone, you use ethylene glycol, the diol, and acid. No water allowed. Second one, we need a Grignard that is, or I mean, sorry, we need an oxidizing agent that stops at the aldehyde. The Grignard reagent, we need 2 carbons, so make sure it's MgPr with an ethyl. Step 1, step 2, mild acid. And then last but not least, need to deprotect. And that's where you put on acid water and take it back off. Okay, so first step, that as mentioned. Second step, PCC, chromate with pyridine. Step 3, the Grignard reagent we just mentioned, followed by acid, workup. Notice I put the wrong solvent in here. If I do that, it will catch fire. There'll be fire everywhere. It'll be terrible. So it has to be an ether. And then finally, mild acid to work it up. Not bad. Synthesis isn't bad, but we did synthesis with alkenes. We did synthesis with SN1, SN2, elimination. So you got the overall big picture of things, but now we're going to add nuances of when we have multiple functional groups. How do we protect one and react at the other one, and then deprotect in the end? Always practice safe chemistry. Always put your protection on first thing you go into lab, and take it off before you leave lab. You don't want to walk out with gloves and lab coats. You will transmit chemicals to the rest of the world. So this hopefully was a pretty good summary. We're getting along quickly. 2 more podcasts in the alcohol/carbonyl section before we go to hardcore carbonyl reactions. So thank you as always for sticking around for the podcast, and hopefully I will see you at the next one. Bye.